Welcome to my file on the changing atom. We're going to look at how the model of the atom has changed over the years and how it continues to do so. So to start off with, we're looking at the Greek atom. So in the 5th century before Christ, the Greek philosopher Democritus developed the first idea of the atom. He thought matter was made out of particles, and he suggested that you could divide a sample of matter only so many times. Eventually he believed you would end up with a particle that could not be split any further. Democritus called this particle atomos, Greek for invisible. He also imagined atoms were held together by tiny hooks. In the early 1800s, John Dalton developed his atomic theory. John Dalton's theory made a prediction about the atoms. He predicted that atoms are tiny particles that make up elements. They can't be divided. All atoms of a given element are the same, and atoms of one element are different from those of every other element. He used his own symbols to represent atoms of different elements. He also developed the first table of atomic masses. The strength of Dalton's atomic theory is that most of his predictions still hold true today. You can apply Dalton's predictions to much of modern-day chemistry. Between 1897 and 1906, through a series of experiments using cathode rays, J.J. Thomson discovered the electron. Using this discovery, he was able to show that atoms were made up of smaller particles. Scientists had recently discovered cathode rays, but they had no idea what they were. Thomson discovered that cathode rays were in fact a stream of particles. Each particle had the following properties. It had a negative charge, it could be deflected by both a magnet and an electric field, and it had a very, very small mass. Cathode rays were in fact electrons. Thomson concluded that they must have come from within the atoms of the electrodes themselves. The idea that an atom could not be split any further, proposed by the ancient Greeks and Dalton, had been disproved. Thomson proposed that an atom should be thought of as being made up of negative electrons moving around in a sea of positive charge. In Thomson's atom, the overall negative charge is the same as the overall positive charge. This means that the atom is neutral with no overall charge. This model is commonly called the plum pudding atom, as shown in the above diagram. In 1909, Rutherford began work that led to the downfall of the plum pudding model proposed by J.J. Thomson. Two of Rutherford's students, Hans Geiger and Ernest Marsden, carried out an experiment at the University of Manchester. They directed alpha particles towards a sheet of very thin gold foil and measured any deflection or change in direction of the particles. We now know that an alpha particle consists of 2 protons and 2 neutrons. It therefore has an overall positive charge. Rutherford calculated that a plum pudding atom would hardly deflect any alpha particles at all. The results were astonishing. Most of the particles weren't deflected. However, a small percentage of particles were deflected through large angles, and a very few amount of particles were actually deflected back towards the source. Rutherford commented, saying it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. From these observations, Rutherford calculated that an atom's positive charge must be concentrated into a volume much smaller than the size of the atom itself. In 1911, he proposed the following model for the atom. He proposed that the positive charge of an atom and most of its mass must be concentrated in a nucleus at the centre. Negative electrons orbit this nucleus just like planets orbit around the Sun. Most of an atom's volume would be in the space between tiny nucleus and orbiting electrons, and the overall positive and negative charges must balance. He had proposed the nuclear atom. In 1913, the Danish physicist Niels Bohr altered Rutherford's model to allow electrons to follow only certain paths. Otherwise, he argued that electrons would spiral into the nucleus. This was the planetary atom, in which electrons orbited a central nuclear sun in shells. There have, in the 1900s, been further discoveries. So, for example, Henry Moseley, in the same year as Niels Bohr altered Rutherford's model in 1913, discovered a link between X-ray frequencies and an element's atomic number, so its order in the periodic table. At the time, he couldn't explain this. However, in 1918,
Rutherford discovered the proton. We now know the atomic number tells us the number of protons in an element's atom. In 1923, the French physicist Louis de Broglie suggested that particles could have the nature of both a wave and a particle. In 1926, the Austrian physicist Erwin Schrödinger suggested that an electron has wave properties in an atom. He also introduced the idea of atomic orbitals, which we'll learn about further on in the A-level. In 1932, the English physicist James Chadwick bombarded light elements with high-energy alpha particles. He found that a new type of radiation was emitted, much more penetrating than any that had been detected before. He showed this new type of radiation was made up of uncharged particles. Each particle had approximately the same mass as a proton. These uncharged particles became known as neutrons because they had no charge. Further theories have since been proposed for the structure of the atom. It is now thought that protons and neutrons themselves are made up of even smaller particles called quarks. This shows that science does advance. The nuclear model of the atom has now been replaced, and future models will also be replaced as science advances further. We've come a long way from the ideas of John Dalton in the 1800s, and this just goes to show how much scientific change can happen over a matter of 2 centuries.